All right, so now we're going to get into a more realistic situation than what we've been doing before. We're looking now at confidence intervals again for a population mean. So we're trying to estimate the population mean using a confidence interval. This is what we've been doing so far, where we have x bar plus or minus z star times sigma over the square root of n. And the thing I want to point out here is this is the situation where we know sigma. That is, we're trying to estimate the population mean, but somehow we know the population standard deviation. This is not a typical, not a very reasonable assumption most of the time. If you want to find an average height in the population, that's your goal. Most likely you don't know the standard deviation in the population. Okay, so what about the situation where we don't know the population standard deviation? In this case, what should we do? And now we're going to answer that question. Okay, so here's what we're going to do. We're going to estimate the standard deviation using the sample standard deviation. It makes perfect sense. The sample mean is x bar. Okay. The sample standard deviation is computed using your sample size and the x bar to compute it. Okay, makes perfect sense. It's a standard deviation based on the sample. The problem is there's a couple things that happen. We introduce more error. Okay, and depending on the sample size, we get more and more error. That's what's kind of strange about it. Not only is it not the right number, and it actually doesn't do a great job of estimating the real number, okay? It's not the right number, but also the smaller the sample size, the worse the estimation it is, right? So if you have a large sample size, we can assume that sample standard deviation is pretty decent in terms of a way to approximate the real standard deviation. But for a small sample, it doesn't work very well. So here's what we have to do. We introduce a new distribution, because now what we found is that the old distribution is not normal. If we have to use S to estimate sigma, the distribution actually is no longer a normal curve. Instead, it's something called student's t-distribution. Okay? It looks very much like a normal curve, and I'll explain that in a second, but I just wanted to give you a little history lesson, perhaps. It was discovered by a man named William Gossett, and you can look him up if you want. And you notice here it says student. So the great story here is that Gossett worked for the Guinness Brewery and actually discovered the t-distribution as he was trying to improve the quality control at the Guinness Brewery. Okay, so that's where it came from. The reason it's not called Gossett's t-distribution is because the Guinness Brewery would not allow him to publish under his own name, and so he had to use the pseudonym student. That's kind of a cool story. Anyway, so we call it student's t-distribution, or simply the t-distribution, as opposed to the normal z-distribution. So here's what it looks like. You see the solid line right here. This is the normal curve that we're used to seeing. If we look at one of the t-curves here is the dotted, okay, the dashed, pardon me, and the dashed is the t-distribution when we have a sample size of 3. So a sample size of 3 gives us one particular t-distribution. This dotted one is a sample size of 10. That's that t-distribution. So we have various different t-distributions depending on the size of the sample. Okay. So let's talk about, before we go over here, let's talk about how we get this. There are a few things we need to know. The first one is something called degrees of freedom, which I believe we've introduced in the past. Degrees of freedom. And this is simply defined as, I usually use the df n minus 1. That's all it is. When somebody says degrees of freedom and your sample size is 3, you have 2 degrees of freedom. And the way the student's t-distribution works is there are as many t-distributions as there are sample sizes. Okay, so you'll notice that the sample size of 3, which gives you a degrees of freedom of 2, is this dashed line, like I said. What that means is it's a deformed normal curve, basically. What that means is there's more error involved with a sample size of 3 than there is with the dotted line of a sample size of 9, or sample size of 10. Okay, so this is the t-curve with 2 degrees of freedom. We determine these t-curves based on degrees of freedom, not on sample size. And this is 9 degrees of freedom, sample size of 10. Okay? So Gossett probably could have defined these in terms of sample size, but he chose instead to define it in terms of degrees of freedom, which has its advantages too. Okay? All right, so let's look at how we do this now. What's really important is we look at how we actually calculate these things. So here is our confidence interval. And from now on, whenever we do a confidence interval for a mean, we use this formula, not the previous formula. The previous formula kind of gave us intuition. This is the formula you will use. We have x bar plus or minus. Instead of z star, now I have t star. And instead of sigma for my standard deviation, I have s. Everything else is the same. Okay? X bar plus or minus t star times s over the square root of n. Now, t star is the critical value in the same way z star is a critical value, but t star is the critical value for a particular t curve that has n minus 1 degrees of freedom. Okay? The interval is exactly correct when the population distribution is normal and approximately correct for large n, that is n bigger than 30. Okay, so the same conditions apply as before. We have to have a normal curve, or we have to have a large sample size, n bigger than 30. And as a matter of fact, we can relax this a little bit for this distribution. But it works pretty well as long as we have a fairly decent size sample, and 30 is going to be very good. We can deal with fewer in this situation. And we use, to find t star, we use the n minus 1 degrees of freedom. Okay, I'm going to show you how to do this in just a moment, but let's look at this. The differences between these two. We have something called the standard error. The standard error is this bit right here. In the case of the z star that we've been looking at, we had sigma. The only thing that changes now is, now it becomes s. The margin of error used to be the thing on the left, okay, which is the entire plus or minus part, and it was z star times sigma over square root of n. Now the margin of error is t star times s over the square root of n. And the estimate is still x bar. So very, very little has changed. The only hard thing is now we have to use the number we get for s, which is usually a given, in the same way that sigma was a given. So it depends on what the problem is giving to you. We have to now figure out how to find t star. We know to find z star, we look in the table. In order to find t star, we also look in the table. So I'll show you how to do that right now. Here's how we find t star. Here's the table, table C, the t distribution critical values. Okay, so what we've been doing before is we've been going down to the bottom. We're still going to go down to the bottom, and we're going to look for our confidence level. So for instance, if I want a 99% confidence level, or actually let's move this up a little bit. Suppose I want a 90% confidence level. The z star value is 1.645. Okay. Suppose I have a sample size now of 10. Okay. Well, if I have a sample size of 10, I have 9 degrees of freedom. So n equals 10 implies degrees of freedom equals 9. Okay, well let's look at that then. On the left here, you'll notice this column is the degrees of freedom column. So if I have 9 degrees of freedom, I'm looking at this row, okay, row 9, and I'm looking for 90%, which is this column. So I'm reading from the bottom row, okay, and up to the column that corresponds with 9. There we go. So the value I want is 1.833. Okay. So if I have 9 degrees of freedom, that's a sample size of 10, then I use, instead of using the z star value on the bottom of the table, I move up into the table until I get a degrees of freedom of 9. So the z star value would have been 1.645 if I'd known the population standard deviation. If I don't know the population standard deviation, I only know the sample standard deviation, and my sample size is 10, then the value I will use there, my critical value, will be 1.833. Okay? So for the same level of confidence, we get a larger interval because there's more error involved in that calculation. Okay? So that's how we do it. Let's go ahead and do an example, and I'll show you how this works in practice. Here's the example. You're in charge of a quality control at a small facility. In order to make sure that you have the highest quality materials, you test 10 products and measure the weight of the materials. Of these 10 products, the average weight is 4 grams with a standard deviation of 1.5 grams. Okay. So let's look at what we know so far. We have 10 products. Those 10 products have a mean of 4, and those 10 products have a standard deviation of 1.5. Now, the difference between this and problems we've done before is, in the problem we've done before, it would have said these 10 products have a standard deviation of 4, and all products have a standard deviation of 1.5. If the statement had said all products, we would have been looking at sigma. But these 10 products says the sample has a standard deviation of 1.5. Okay? That's why I know this is a sample standard deviation and not a population standard deviation. So here's what I'm going to look at. X bar plus or minus T star times S over the square root of N. Now, we know that X bar is 4. We're going to leave T star blank. We know S is 1.5. And we know N is 10. Now, we also know that the original standard deviation was normally distributed. That's good. We need that in order for this distribution to work. Okay? We want 90% confidence. So when we're doing a t-distribution, we must also know how many degrees of freedom we're looking at. N was 10. That means we have 9 degrees of freedom. So again, we're going to go back to the table we just looked at, and we're going to figure out if I have 9 degrees of freedom and I want 90% confidence, what value am I going to look for? Okay, we actually already know this, but we're going to look at it again, just to be clear. I want 90% confidence, so I'm looking at the 1, 2, 3, the fifth column. That's this 90% here, and I want 9 degrees of freedom. My sample size is 10. So again, I'm going to be looking for a T star value of 1.833. Let's go back to our interval. So T star equals 1.833. So I have 1.833. Okay, so let's go ahead and crunch those numbers real quick. I'm going to have 1.833 times 1.5 divided by the square root of 10. My margin of error is therefore 0.869. So I have 4 plus or minus 0.869. Now what I want to point out here, what's cool about this, the mathematics to get to the interval was a little different than what we did before, but the interpretation of the interval is the same. Doesn't matter how we got there, I have a 90% confidence interval, and this is the 90% confidence interval. What does that mean? I am 90% confident that the true mean is in there. Okay? I've taken into account the fact that I didn't know the population standard deviation. I took that into account. That is accounted for already in my error term here, my margin of error. So once I have a confidence interval, no matter how you get the confidence interval, the interpretation of the interval remains the same. That's why we spent time on it this last week. Okay, so here's what I say. I am 90% confident that the true mean, the true average weight of this product is 4 plus or minus 0.869. So in repeated samples, every time I get a confidence interval, 90% of the confidence intervals I will create will have the true mean inside of it. Okay, so let's look at a quick summary. This is a really important thing that I'm going to look at. I'm going to emphasize several times as we go on. I'll mention it once now and ask you guys to have it down in your notes somewhere. This is the how to write it. This will be true for everything we do for the rest of the course. 4 things. First thing you do is always determine which procedure you need to use. Tell whoever's reading the question, this is what I'm going to do. I'm going to do a confidence interval for means using a t-distribution. That's what we just did. Number 2, check the conditions. Do you have a normal curve? Do you have a large sample size? Can you do the procedure? Number 3, find the interval. Give me the actual values from left to right. Okay? And 4, interpret the result in context. You don't get credit unless you can say what it means. So here's breaking these down again, right? First thing, say that we're doing a confidence interval for means if that's our situation. Check your conditions. Explain, do we have a simple random sample? That's what it says. Why can you assume independence? Because we have a simple random sample. Why can you assume approximate normality? Okay? Perform a calculation. Do the math, okay? if you're doing a t-curve, you must write down degrees of freedom. Okay, that's an important part. You need to write down what is going into the formula. Don't just give me an interval. Say this is x bar, this is s, this is n, these are my degrees of freedom. And then finally, interpret the resulting context, answer the question that was asked. Okay, we're going to go over this quite a bit more in class, but now we've got our first complete theory here for inference. All right, good work, everybody.